On the left, 3 data points and the best fit line. On the right, a vector dropping perpendicularly onto a plane. These two pictures look nothing alike, but they are the same problem connected by a single right angle. By the end of this video, you'll see why the best fit line is really a shadow, a projection, and why the error in both pictures points in exactly the direction it must. Let's make this concrete with 3 data points. The point 1, 1, the point 2, 2, and the point 3, 2. We want the best fit line y equals c plus d times t. Plugging each data point into this model gives us 3 equations. From the first point, c plus d equals 1. From the second point, c plus 2d equals 2. From the third point, c plus 3d equals 2. Now let's stack these into a matrix equation. Ax equals b. The matrix A has rows 1, 1, then 1, 2, then 1, 3. The vector x is the column vector cd, and the vector b is the column vector 1, 2, 2. Notice that A's first column is all 1s, and its second column holds the t values. 1, 2, 3, we have 3 equations, but only 2 unknowns, so this is an overdetermined system. No single pair CD can satisfy all 3 equations exactly. Picture 1, the data space view. We plot the 3 data points on a scatter plot, the point 1, 1, the point 2, 2, and the point 3, 2. The best fit line turns out to be y equals 2/3 plus 1/2 t. Let's find the fitted values on this line. At t equals 1, p1 equals 2/3 plus 1/2, which is 7/6. At t equals 2, p2 equals 2/3 plus 1, which is 5/3. At t equals 3, p3 equals 2/3 plus 3/2, which is 13/6. The errors are the vertical gaps between the actual data points and the fitted values on the line. E1 equals 1 minus 7/6, which gives us negative 1/6. E2 equals 2 minus 5/3, which gives us positive 1/3. E3 equals 2 minus 13/6, which gives us negative 1/6. Least squares minimizes the sum of the squares of these gaps. E1 squared plus E2 squared plus E3 squared. Now forget the scatter plot. Here's a completely different picture of the same problem. We move to R3 where every vector has 3 components. The matrix A has 2 columns. A 1 equals 1, 1, 1, the column of 1s, and A2 equals 1, 2, 3, the column of t values. The column space of A is the set of all vectors of the form C times A1 plus D times A2. This is every possible output AX as X varies. It traces out a 2-dimensional plane through the origin in R3. Now plot B equals 1, 2, 2 as a point in R3. It sits off this plane, and that is exactly why no exact solution exists. We need to check, can we write B as C times 1, 1, 1 plus D times 1, 2, 3. Setting up the equations, we get C plus D equals 1, C plus 2, D equals 2, and C plus 3, D equals 2. From the first 2 equations, D equals 1 and the C equals 0. But then the third equation gives 0 plus 3, which is 3, not 2. So B is definitely not in the column space. The projection P is the closest point in the column space to B. Drop a perpendicular from B down to the plane. It lands at P equals 7/6, 5/3, 13/6. These are the same fitted values from picture 1. The error vector E equals B minus P, giving negative 1/6, 1/3, negative 1/6, the same residuals as before. Let's confirm E is perpendicular to the column space. E dot A1 equals negative 1/6 plus 1/3 minus 1/6, which equals 0. E dot A2 equals negative 1/6 plus 2/3 minus 3/6, which also equals 0. So E sticks straight out from the plane like a flagpole, perpendicular to the entire column space. Both pictures give the same numbers. The insight is Y. It comes down to a right angle. Check P dot E, 7/6, times negative 1/6 plus 5/3 times 1/3 plus 13/6 times negative 1/6. That's negative 7/36 plus 20/36 minus 13/36. That equals 0. Good, but not enough. The error E must be perpendicular to every vector in the column space. Check E dot A1, negative 1/6 times 1 plus 1/3 times 1 plus negative 1/6 times 1. In 6, that's negative 1 plus 2 minus 1, all over 6. 0. Check E dot A2, negative 1/6 times 1 plus 1/3 times 2 plus negative 1/6 times 3. In 6, that's negative 1 plus 4 minus 3 all over 6. 0. Both columns give 0, so A transpose times E equals the 0 vector. This is the real condition. And this rearranges to A transpose A times X hat equals A transpose B, the normal equations. Now return to the split screen to see the key insight. In picture 1, the data space, C equals 2/3 is the y-intercept and the D equals 1/2 is the slope. Together, they define the best fit line. Y equals 2/3 plus 1/2 t. In picture 2, the vector space, the projection P equals 2/3 times A1 plus 1/2 times A2. The same C and the D now serve as weights that combine the column vectors to reach P. Take a moment to appreciate this. The exact same numbers, 2/3 and 1/2, play completely different geometric roles in each picture. In picture 1, they tilt a line through the data points. In picture 2, they scale and add column vectors to reach the nearest point on a plane. Same numbers, two entirely different geometric meanings. Here is a common confusion that trips up many students. You might check that P dot E equals 0 and stop there, thinking you're done. But that's not enough. Many vectors in R3 are perpendicular to P, but not perpendicular to the entire column space. Picture the column space as a plane, with P shown as a green arrow lying on that plane. Now imagine an orange dashed vector E prime emanating from the tip of P. This vector forms a 90-degree angle with P. You can see the angle marker, but it is clearly tilted. It is not perpendicular to the plane surface itself. This vector E prime is perpendicular to P, but E prime does not lie in the orthogonal complement of the column space. This is the wrong error vector. It corresponds to a different, worse approximation. Now let's fade that away and look at the correct picture. The correct error vector E is shown as a solid red vector pointing straight up from the plane, perpendicular to the entire plane surface, with the right angle marker at the plane. This vector E is perpendicular to the column space of A, and this is the correct error that minimizes the length of E. On the right, notice the distinction. The condition P dot E equals 0 is labeled as weak and not sufficient, shown in yellow. The condition A transpose times E equals 0 is labeled as strong and what we actually need, shown in green. A transpose E equals 0 means the error is perpendicular not just to P, but to every direction in the column space. That is what guarantees we have found the closest point and the shortest possible error. Here is the two-picture correspondence that ties everything together. In the data space, our data points 1, 1, 2, 2, 3, 2 correspond in the vector space to the vector B equals 1, 2, 2. The fitted values that lie on the best fit line correspond to the projection P. The vertical residuals, E1, E2, E3, correspond to the error vector E, which equals B minus P. The best fit line itself corresponds to the column space of A. And minimizing the sum of squared errors is exactly the same as minimizing the squared length of E. In both pictures, the error is perpendicular to the space of things you can control. E is orthogonal to the column space of A. It is the same right angle seen from two different windows. That is the geometry of least squares, and this projection idea generalizes far beyond fitting lines. It extends to planes, polynomials, Fourier series, and any linear model you can imagine.